Yeah.
Okay, let's get started. So it's a pleasure today to have with us Ira Wasserman. He's visiting from Cornell. So Ira got his PhD at Harvard. He then moved to Cornell for a postdoctoral position, and he has been there since then. He then became a professor there. He's interested in the physics of neutron stars, in addition to observational constraints of the universe. He's going to be with us for 2 days, and he's going to tell us today about the rotational dynamics of neutron stars.
Thank you, and thank you for not saying the date of my PhD. Okay, so I'm going to talk about actually only part of the work that we've done over the last few years on dynamics of the R mode and stability of neutron stars, and an array of former and, well, none of these are current Cornell graduate students have worked on this topic, starting with Katrin Schenk, John Drew Brink, who's still at Caltech. I'd like to point out that Katrin is now a biologist, so you can work on neutron stars and become actually she's a neurobiologist. John Drew Brink, Phil Aris, who's I believe has visited here from time to time when he was at KITP. And much of what I'll talk about is recent PhD thesis work by Ruxandra Bondarescu, who's now at Penn State. I should have changed that. And of course, you all know Sharon Morsink. She's a renowned relativistic astrophysicist at Alberta, and Aina Flanagan and Saul Tukolsky at Cornell. So I'm going to start out with some background, which I will go through rather quickly because I know this audience is well familiar. But for those who aren't, neutron stars in some respects are giant self-gravitating nuclei. Their properties are somewhat uncertain because their mean densities are already 2.5 times nuclear, and therefore their central densities are actually even larger. They can rotate by a crude Newtonian argument up to frequencies as fast as 2,000 hertz. That is about a half a millisecond period. Now that's a Newtonian argument. Actually, in general relativity, it's a bit more complicated than that. So this is a table which is still pretty representative from work done in the 90s by Greg Cook, Stu Shapiro, and Saul Tukolsky. These are various equations of state of nuclear matter. Doesn't matter what these names mean. They tend to refer to nuclear potentials or a method. This is relativistic mean field theory. This is mean field theory. B here is beta, J is Johnson. 1 and 5, I don't remember. I think it has to do with whether there are condensates or not in the core. And then there's another potential called the Reed potential that people talked about then. The important thing is that these tend to range from what's called relatively soft, which means you have relatively small radii, small masses, to relatively stiff. And here are the maximum masses and spins. And you'll notice that I have 2 columns here, absolute and normal. And this is actually a relativistic effect. So the absolute means if you took these equations of state and you found absolutely the maximum mass and maximum spin, those are the numbers that you would get. And the way that these calculations typically are done is by looking at sequences of fixed baryon number. Okay, and then working out the mass as a function of spin rate. There are some sequences, though, that do not have non-rotating endpoints. Okay? And that's why this column is different from these 2 columns. The normal sequences are the ones that you could spin up at fixed baryon number from 0 spin until ultimately it reached some form of instability, either to collapse or to break up. So those are often called normal sequences. And needless to say, these have lower spin frequencies than those. But you can see that although you don't get 2,000 hertz for any of these numbers, you do get numbers between 1,000 and perhaps 1,700 hertz. So the Newtonian estimate isn't right, but it isn't terrible either. For 1.4 solar mass neutron stars, and many neutron star mass determinations that we have are in that range, you see that obviously you typically get lower frequencies. But you can still have frequencies as high as, say, 1,400 hertz or so. OK. I'm going to skip the brief history since you all probably know it. Neutron stars, I think it was the old saying of Zeldovich's, if I remember right, were discovered at the tip of a theorist's pen, that theorist being most likely Lev Landau. And it took a long time after the theorist's pen discovered them for astrophysicists to discover them. It was about 35 years. But now we know a lot of neutron stars. This isn't even a complete compilation. These are mainly, I guess, the radio pulsars. And pulsars, this is from a compilation by Kramer. Pulsar astronomers like to plot this on their own sort of HR diagram, except for them it's the period derivative, a dimensionless number, d spin period d time. And that's logarithmically plotted here. And here are the periods in seconds. Most neutron stars are in the sort of secondish part of this curve with lifetimes. They spin down with time, and they have lifetimes like 1 million years, 10 million years, 100,000 years. And then there are the very fastest ones, the millisecond pulsars, that live longer. They spin down slower. And the interpretation of this is that they're also less magnetic, and that fundamentally the energy that's radiated by neutron stars, the source of the energy is the rotation of the star, but the mechanism by which it radiates has to do with its magnetic field. I also want to, this is a famous sort of pie chart that I don't see his name anywhere here, but I believe this is from Danny Podge. And it shows you that although a neutron star may superficially be a cold, compact object made of nuclear matter, it also has considerable complexity, and there's a lot of uncertainty connected with the properties of the neutron star. So moving outward, we're least certain about the characteristic of the core. In fact, at lunch today, some of you were asking about quark matter. That's one possibility. More or less speculatively, people talk about hyperons in the core, and I will use the hyperons later on in this talk for a dissipation mechanism. Then as you go out, there's an outer core. And here, fairly uncontroversially, there's a proton superconductor, we think. A little more controversially in the outer core, there may be neutron superfluid. And when they're coincident with one another, there's a lot of interesting stuff that goes on because the magnetic field will become organized into proton flux tubes in the superconductor. The circulation of the star, which is principally neutrons, is organized into neutron vortex lines, and they interact. It turns out the vortex lines can become magnetized through a mechanism I can talk about later, but isn't particularly germane to what I'm the main goal of my talk. In the crust of the neutron star, which also has interesting uncertainties associated with it, it's also thought that there's a distinct neutron superfluid with a different pairing character for the Cooper paired neutrons. And it's thought that this neutron superfluid, which coexists with a crust which is basically a crystal made of bizarre atomic nuclei, which have strange shapes and don't appear in the usual periodic table, they're heavily neutronated. It's thought that these neutron vortex lines tend to pin to the nuclear crystal, and there's evidence for that from trying to understand another feature of rotational dynamics of neutron stars, namely their behavior after a phenomenon called the glitch, which is a discontinuous change in rotation of the neutron star, which is observed in quite a few pulsars now. It also flies in the face of something else I won't talk about, which is neutron star precession. I will tell you that I've spent a lot of time thinking about that problem, but I don't spend a lot of time talking about it in public, partly because I once wrote a very detailed and learned paper saying that the phenomenon which appears to be observed is impossible. Okay. So you may be wondering why you should be listening to me at all if I write papers like that. So I'm going to focus only on the fastest rotating neutron stars and a couple of questions that come about to do with those. So the easiest to determine neutron star rotation rates is done in radio astronomy. And really here, the only thing to really remember is that the record, which was set only maybe 3 years ago, is 716 hertz. Okay, that's a spin period of about 1.4 milliseconds. The B and the GC says that it's in a binary star system and in a globular cluster. The record that was broken was held by 1937 plus 21 since 1983 when it was discovered. So evidently, even though there have been loads of searches for fast rotators, there aren't many around. This one happens to be isolated. Then there's another one which was discovered around 1990, which rotates at 622 hertz. It's also in a binary, and this one's interesting because it's evaporating its binary companion. And so you see a lot of B's in this table. That all means binary. You also see GCs saying they're in globular clusters. There are a lot of millisecond pulsars in globular clusters, and they're either in binaries or we think they used to be. And in a second, I'll remind you of the connection between binaries and fast rotation.
So AD means it's like the 30th?
I'm sorry?
The AD notation means it's the 30th pulsar and that globular cluster?
Yeah, probably, yeah. Yeah, I'm not as quick as you, Wei-Li, at doing the counting, but there are many, many. And many of these are in the same cluster. You can see these are the coordinates. Okay? So, and I forget which one it is. It might be, well, I wouldn't even try to remember. I'm not good at that. So what's the binary? But the answer is yes. There are loads and loads of them in individual globular clusters. So the connection between binary star systems and fast rotating neutron stars also has been well known since, for the last 20-something years. The idea is that you have a neutron star paired up with some sort of normal star, accretes matter from it. It's in a close enough binary that matter is pulled off the normal companion. It has high specific angular momentum, so it forms an accretion disk, and the disk matter spirals in viscously until it can accrete onto the neutron star. And as it accretes onto the neutron star, it both increases its mass and increases its rotation rate. It's not that hard to speed up the rotation rate to roughly something like 2,000 hertz. All you need is to increase the mass of the star by something like 30 to 40%, depending on various parameters, like how close to this maximum you would like to be and where the inner radius of the accretion disk is. So one question is, we see the fastest neutron star to be 716 hertz. Why don't we see faster ones? There are plenty of equations of state of nuclear matter for which you could have faster ones. And in fact, I think most people would say that the cases where you could not are probably exceptional. You can also study this in general relativity also from these papers in '94. There are other factors you could put into these studies. So what these guys did was they imagined an accretion disk around an accreting neutron star extending to its innermost stable circular orbit, determined instantaneously for the mass and rotation rate of that star. And they then kept adding mass and angular momentum until they reached from a 1.4 solar mass starting point, until one of two things happened. The star became stable either because it started to shed mass or because it collapsed. And here you can see that for these equations of state, that typically you get 1660, 1120, and so on. You can get, in this one case, something just a bit above 700 hertz, and it's conceivable that the answer to why we don't see anybody rotating faster than 700 hertz is that this equation of state, which I'll tell you from a theoretical point of view is not particularly self-consistent, by some accident is roughly correct. Okay, the italicized guys turn out to be endpoints, the slanted guys, that are on sequences that have no non-rotating endpoints. So as these guys spin down with time, no matter how long it takes them, they'll reach a pretty spectacular end. Okay, now another answer to why we don't see fast rotating neutron stars that I believe was first put out by Bob Wagoner in 1984 and in a different context by Lars Bildsten in 1998 is that gravitational radiation reaction limits the rotation rate of neutron stars. And the idea is simple. You spin up via accretion, and here I'm taking the accretion to be roughly to the surface, which for low magnetic fields isn't bad. You spin down via gravitational radiation. There's some non-axis symmetry of the star, epsilon times the moment of inertia. And you can balance these two and ask how non-axis symmetric the star has to be, and you get an epsilon of 10 to the minus 7 for a reasonable mass accretion rate of about 10 to the minus 9 solar masses per year. And at the time that both Bob and Lars were interested in this, they were wondering mainly about spinning up to 300 hertz, not all the way to 700. So 10 to the minus 7, it's a tenth, it's like a tenth of a centimeter bulge in a neutron star. But then the question was, what was the source of Q? And they had different ideas, which I could talk about a little bit later on about how that would happen. And there are other ideas that people talk about now, like magnetic mountains. I should also say that there have been attempts to using LIGO to put limits, which you can do, by searching for gravitational radiation for certain known neutron stars, and the limits are not that good, as I recall. Another possibility is that, although it's suppressed, is that you can get gravitational radiation from currents, from perturbed flows inside neutron stars. And since those are no longer the leading multiple for the gravitational radiation, it's suppressed by v rotational over c squared. And there's also an amplitude squared, which is basically delta v over omega r squared. Okay? So then you can also get a condition for balance, and it seems like it ought to be possible to satisfy it. Delta v over omega r of about 10 to the minus 6 for similar parameters. And the question here was, what was the source of the currents? And soon after, actually, Bildsten's 98 paper, people began to talk about the CFS, or Chandrasekhar-Friedman-Schutz, instability of a particular kind of mode of neutron star called the R modes, or Rossby line. Now, almost 40 years ago, Chandrasekhar talked about these instabilities in a generic sense. So let me basically give his kind of argument. Suppose you have a normal mode with a velocity perturbation like so, where omega is the frequency in the inertial frame of reference, and I'll take that to be greater than 0. You could do the same argument with the opposite sign. So in other words, prograde in the inertial frame. In the rotating frame, the same mode has a frequency omega minus m times the rotational angular velocity of the neutron star. And even though the inertial frame frequency is greater than 0, this can be greater than 0 or less than 0, depending on its actual value. So now if you look at the energy in the rotating frame, which is E minus omega jz, where z is the direction of rotation and j the angular momentum, and you use the fact that gravitational radiation radiates both energy and angular momentum, and they're related like so, you find that the energy in the rotating frame changes like sigma over omega times the change of the energy in the non-rotating frame. And these can have opposite signs. So even though you are losing energy, E dot, in the inertial frame, the rotating frame energy could be increasing. And that's basically the connection. That is, retrograde rotation in the rotating frame implies instability. And this is what Chandrasekhar talked about in 1970. And it's an example of what I think the plasma physicists especially call negative energy instabilities, which sounds like a sort of strange term. But wind over water is another example where basically a drag, a dissipation, leads to an instability. Now, the R modes are a subset of a whole big class of modes sometimes called inertial modes or rotational modes of rotating stars, where the restoring force is the Coriolis force, and they have a particular character. They're what are called axial modes. They're displacement fields or the curl of a vector field. And these are modes that are prograde in the inertial frame and retrograde in the rotating frame. So they're subject to this instability. And so Nils Andersson, Lars Bildsten, John Friedman, and Sharon Morsingel about the same time said this might be why you get currents that produce gravitational radiation reaction capable of limiting the spins of neutron stars that you can get from the spin-up mechanism. So time permitting, I'm going to actually talk about these three questions. The first is the one I just said, what stops spin-up? I'm going to talk about that second, even though I typed it up first. I have to apologize to you. I'm now the chairman of the astronomy department at Cornell, and so I do everything backwards. So I do I tell you what I'm not going to do first, and I find that's a really good strategy with my faculty. Okay, so I'm going to talk about what stops spin-up if I get time to do that. And what I'm going to spend more time is a paper that Ruxandra Bondarescu, Sol Tukolsky, and I just finished fairly recently, which is another question, which I didn't say much about when I showed you the PP dot diagram. But as it turns out, there's people who do population studies to try to understand how that collection of neutron star spins and spin derivatives came about. Although I've told you a bit about the fast end, for the big block, the 1 second, people have done very comprehensive studies, and there's no obvious reason that you had to have any of those born rotating particularly fast. And by that I mean, even the Crab pulsar, which is currently rotating with a period of 33 milliseconds, if you just extrapolate back its spin down, it's maybe 15 milliseconds. You don't need it to be rotating at 1 millisecond or a half a millisecond or anything close to breakup. But you could ask whether that means that it truly was born rotating only at 15 milliseconds, or could it have been born rotating much faster and in a very, very short period of time, long before you ever saw it with a radio telescope or magnetic dipole spin down became all that was going on. The star may be spun down very quickly. So that's something the R modes might be able to do. So the question I'm going to talk about a bit now is, could you have been born extremely fast and relatively quickly become slower? And I'll tell you the answer is going to be sort of incomplete. And then the third question is, if any of these things happen, could you observe the gravitational radiation that's produced? So you have an instability, and the question is, what amplitude does the unstable mode reach? And there are several reasons this is important. One is that if you're looking for gravitational radiation, the wave amplitude is proportional to the amplitude of the wave, of the mode. If you're looking at the thermal evolution, the heating goes like amplitude squared. And it turns out direct hydrodynamics, not so easy to do what you need to do for a couple of reasons. One is the R mode instability grows rather slowly. You'd need to be able to do a simulation for tens of millions of rotation periods. And also, as it happens, the modes that the R mode wants to couple to non-linearly turn out to be on small scales. And that means there's a resolution challenge. So what I'm going to talk about now is the three-mode problem. It's the easiest nonlinear model that's physical. It might be enough, and I'll show you in some cases it may actually be. It's kind of a prelude to looking at multi-modes, but I'll tell you we did the multi-mode first. So if I don't get to it, we did a simulation with 5,000 modes. It's pretty big. So I might talk about that if there's time, but there probably won't be. We have heating and cooling. The heating is from the modes dissipation, and the cooling is neutrino cooling. There are two nonlinear effects that I'll talk about that are very important. I'll show you examples. One of them is parametric instability, which I'll explain momentarily, and the second is a fixed point. And most important, which is something that motivated us from the start, is that as engineers know, when you have a lot of modes that are densely packed in a finite region, you get a lot of resonances. And when you get resonances, nonlinear effects become important at small amplitudes. And so some of the amplitudes I'll show you are really small. So I'm not going to show very many equations, but I thought I'd show you these. So if you take a three-mode problem where you just have three-mode interactions, which is all I'm going to look at, you can write the dynamics in terms of action angle variables. The action is basically proportional to the amplitude squared, and the angle is the phase of the mode. And you end up getting four coupled equations. R is the R mode, 2 is one of the daughters, 3 is one of the other daughter. And all that you need to compute here is the relative phase, phi r minus phi 2 minus phi 3. If these gammas were 0, this is a Hamiltonian system, and this is the Hamiltonian. These three are just the linear harmonic oscillator written in action angle variables. And this is the three-mode interaction. Okay, you can check that. I've checked it. The R mode amplitude is unstable, so it will grow at a rate 2 gamma r. And the others tend to be stable and will grow will shrink at gamma 2 and gamma 3. So parametric instability happens. Suppose you start out with the daughters and the R mode low amplitude. I'll show you, I solved these equations on the computer to show you an example or two. The R mode will grow linearly because it's unstable. The daughters will shrink linearly because they're stable. But when the R mode amplitude gets big enough, it can overcome, I'm sorry, I should go down here. This positive term can overcome this negative term and cause growth. That's called parametric instability, and you can work out the threshold for that. And it's proportional to the product of the daughter mode dampings and inversely proportional to the coupling. Obviously, the weaker the coupling, the less likely this is to happen. And then there's this 1 plus delta omega over gamma 2 plus gamma 3 squared. And eventually, the R mode will reach that. And to give you the punchline, usually it doesn't get much beyond that. And that's a fairly small amplitude. Steady state is a little bit different. What ends up happening there is that you just set all these time derivatives to 0 and solve. And you get that the products of the gammas times the amplitudes are all the same. And they're gamma r, gamma 2, gamma 3 over 4 kappa squared. And the delta omega depends almost the same. Often in our simulations, gamma r is small compared to gamma 2 or gamma 3. And so a little bit after you pass parametric instability, you get into the steady state. But not always. And I'm going to point out to you that it's possible for this number to get real big. Okay? That is what happens when we get runaways. If you start at the steady state and perturb it slightly, stability only depends on these parameters. Delta is delta omega over gamma 2 is this thing. And linear stability analysis tells you when that's bigger than 1, you'll be linearly stable. But that's far from the whole story. Okay. So here's an example. I slapped together a computer program in preparation for this seminar.
Can you discuss a little bit what becomes cap in this context?
Yeah, it's basically like a matrix element between the displacements of 2, 3, and R. I mean, it's more complicated than that. There are about 8 terms that go into it, which we developed in some detail in a paper in 2000. But it's basically a form of matrix element, a 3-way matrix element. Another way of putting it is what we did was you can write down in the inviscid and stable limit, you can write an action principle for hydrodynamics, which we did, and then we expanded it to third order and worked out the coefficients that you would have in those terms. But there are a lot of subtleties that are involved in doing that, as I'm sure you would imagine. So here's an example that I did where this is the amplitude of the R mode scaled to the fixed point. And I took the daughter modes to be identical for this example. My program doesn't have to do that, but I didn't want to graph 4 things. So this is the amplitude of the daughters, which I took to be identical. And they also start out, in this case, at very small amplitudes. So the first thing you see happens, and this is the value of delta, so it's linearly unstable at the fixed point. And this is not an unrepresentative ratio of daughter to R mode damping rate for newborn neutron stars. The R mode instability growth rate can be rather small compared to the daughter dissipation. So the R mode grows up. I didn't plot it here because you'd all laugh at me, but the daughters are going down to like e to the minus 5,000 or something before anything happens in this case. So the R mode goes up. It passes the parametric instability threshold. And then the daughter says, even though I'm now at e to the minus 5,000, I'm going to zip up. And in this case, you'll notice that partly because you're in the linearly unstable regime, the dynamics get rather complicated. And you see the R mode does this sawtooth thing. And you can probably see that it's multiply periodic, sort of. And the daughters are spiky. And the relative phase, is also spiky and doing odd things. Okay? Now, one thing that's worrisome about, well, let me say 2 things about this. First, it's not running away. It's in some sort of nonlinear cycle. Okay? And the second thing is that since gamma daughters is so big, most of the dissipation is in the daughters, and it's very spiky. So that might worry you, because it worries me. These are the same parameters, actually with a slightly different initial conditions, but it has the same character. This is a smooth average of the amplitudes, averaging over the spikes, and they're pretty stable. And the reason that I'm plotting that is that it turns out that sort of generic, how much time do I have? Am I almost done? 15 minutes, oh, okay. I can talk a little slower. Okay, I think I'll come back to this one. It's in a different regime. So for the newborns, just an overview of the dynamics, it turns out that parameter delta, which is the detuning divided by gamma 2 plus gamma 3 minus gamma r, can have almost any value. Okay? In fact, it can even be negative. I'll show you a little bit of that in a second, or at least I'll say it qualitatively. In the accreting case, which was what that previous graph, this one, was relevant to, it's much more stable, you can see. Delta tends to be big, and the R modes and the daughters tend to have similar growth rate dissipation. They're not wildly different. So in that case, delta tends to be much greater than 1 generally, which means that the fixed point is very linearly stable. For the newborns, it's basically a complex show, and it could be almost anything. Okay, we have heating from the modes, as I said. So now I'm going to talk about the newborns. And this is a cartoon of the different kinds of behaviors. At high temperatures, the dissipation is dominated by bulk viscosity. We modeled what we did on work by Ben Owen on bulk viscosity from hyperons in the core of the neutron star. And at low temperatures, you have boundary layer effects, which augment the shear dissipation damping. So basically, you have an Ekman layer that you would have an Ekman layer forming where you would have a lot of dissipation if the neutron star crust were really monolithic and rigid, but it's not. So in fact, you end up getting something that's a little bit weaker, but still more dissipated than just shear viscosity. This curve is the stability curve, where the growth rate of the R mode and stability equals the dissipation rate. And this shows various possible evolutions. So we start these guys like way off here somewhere. And way off here somewhere, the dissipation is low. That's why the R mode stability curve is so low. And in fact, we can even start out with situations, and at high enough temperature it would be true, where that parameter delta would be negative. That is, the R mode instability would be growing faster than the daughters could dissipate. That's an extremely unstable situation if you can grow to large amplitude. So the tendency for the newborns for a neutron star is it wants to go to the left. It wants to get cooler. It's radiating neutrinos away. It's only the dissipation from the R modes that can stop that and cause anything else to happen, or not just the R modes, but also the daughters. So one type of evolution, which is actually the most promising for gravitational radiation, we call type 1. And so you're cooling, 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 cooling. You reach a point where the growth rate of the R mode instability times the cooling time is about 1. Soon thereafter, the R mode amplitude starts to shoot up. It hits parametric instability. And at that point, it may or may not be at a large enough amplitude to stop the cooling. But if it isn't at a large enough amplitude to stop the cooling, it'll just keep moving this way. Okay. It'll keep moving this way to lower temperatures where the dissipation rises, and you can see that qualitatively because this curve is going up. And so the amplitude goes up, and the cooling is actually decreasing rapidly because it's a high power of temperature, plus there are suppressions from superfluid effects. And eventually you reach a point where they're in balance. And when that happens, you descend this cooling equals heating curve until you hit the stability boundary, and then off you go.
In this early regime, you're still only considering, say, the coupling to a couple of daughter modes.
Just two. Just one triplet.
Wouldn't that eventually change significantly if you had coupling to many daughter modes?
It might. When we...
There's very strong damping of it at this point.
It might. I'd love to answer that at length. So maybe after, why don't you ask that and we'll talk about that at length. The short answer is I'm not sure exactly what will happen, but the long answer is I have some ideas about how that works. So, and one of the things I've been thinking about, in fact, is to put in all the possible daughter couplings. But, okay. So another possibility is that you come across here and you never grow to large enough amplitude on this side of the stability curve. And what usually happens then is you keep going across overshoot and you tend to come back. You then cross back and forth and descend this curve. We call that type 2. We're really imaginative in our labeling. And then another one is that you don't do that at all and you descend type 3. So let me show you type 1, because type 1 already shows you some of the interesting features. And I may have to flip. I am a bit worried about that. So you go across, in this case. This is what we call a type 1 evolution. And these temperatures here, this is the proton superfluid critical temperature, which we fixed at 5 billion degrees. One of our goals, I have another student working on this, is to explore how the parameters enter into this. And the hyperons in the core are also superfluid, so we took their critical temperature to be 2 billion degrees. It's a reasonable number, according to estimates, but all of this is very uncertain, which is why it's good to try to get some qualitative feel for the evolution. So across you go, you reach this point A, and point A is where heating and cooling can first come into balance. You're at the appropriate fixed point. And in fact, if you work out that parameter delta here, well, Ruxandra and I actually disagree on the value, so I'll tell you mine. It's 2.17, so you're linearly stable. And then you go down, and so you can see, so the dashed line is actually integrating the equations that I put up, plus the heating and cooling equation, plus spin down, which is happening both by gravitational radiation and also magnetic dipole spin down. And the dots are just assuming that you're always at the fixed point. So it looks pretty good. But if you have good vision, you'll see that the dashed line is basically a line until about here, when it starts to fuzz out. So what happens here is that parameter delta starts to drop below 1. The fixed point becomes linearly unstable, and you get one of those ratty sawtooth things. Then eventually you get down to the stability curve at B, and you spin down, never to be unstable again. Yes?
So this is, you consider the same thing, interaction of modes and quasi-steady evolutions, and you parametrically changing parameters?
Yes.
Okay.
Yes. So the temperature and spin rate are changing, but you're sitting on that curve. So that's what the dots are. Okay. So I actually blew up this curve just to show you what's happening. So when you right around here, you first entered that curve. And you can see that you must be pretty linearly stable because you can't really see much amplitude. And then all of a sudden, bang, this horrible crap switches on. Okay? Now, the odd thing about it is that the amplitude of these wild oscillations seems to be going down with time. And you would have said, well, it's really unstable. What's going on? And in fact, that parameter delta is getting smaller as you go down the curve. And what's going on there is that, yes, you are wildly unstable as you move down this curve. But the amplitude of the oscillations is related to the amplitude of the fixed point, and those are going down as you go down the curve. So I think that's what the explanation is for that, although I'm not sure of it. And then you can see at the end there's a plummet, and that's just that you entered the stable regime. What I mean is the R mode is stable, so all the amplitudes drop. Here all we did was we raised the hyperon superfluid temperature. And you can see that this one is ratty all the way down. And if you work out that same parameter delta, it's less than 1 up here. Okay? You then cross over, you overshoot, like as I told you, and then you descend this curve, a regime that actually Bob Wagoner talked about some years ago. And you can do a lot of things. Sometimes you come across, you get trapped in this curve. I'm not sure about what this instability is exactly. It might be thermal. But it could also just be nonlinear. I haven't settled that in my own mind yet.
So gravity waves, the most interesting regime is what, on the left side?
On the right side. It's that type 1. So I'll focus on that actually in a minute. But this is the longest lived and highest amplitude side. Okay, and then you can get onto this curve and go down. So here are the gravity waves. This is actually for one of those so-called type 1s. That is this sort of behavior. There's a crossover where, so what's shown here is h in units of a couple by 10 to the minus 26 at a distance of 100 kiloparsecs. We fixed the hyperon superfluid temperature at 2 billion degrees. The amplitude will depend on that as a function of time. And we show both frequency and amplitude. Actually, this is just the amplitude. I didn't bring the frequency curve. But the frequencies are going down as you go up in time. And you can see that the curves with higher dissipation, we have a parameter that governs it, and here it's 5 and there it's 2.5, have larger amplitude and therefore larger h. But the lower dissipation ones, partly because they have lower amplitude, actually live slightly longer. There's also a magnetic field effect. If the magnetic field is too strong, it dominates the spin down no matter what the gravitational radiation is doing. 10 to the 11 Gauss is roughly, in this case, you're just seeing gravitational radiation spin down. And it's the longest lived case. And if you actually look at our paper, you can see that we can get this part of the curve to live for decades. And these kinds of H's are well within what advanced LIGO should be able to do. There is a problem which I don't know the answer to yet, and I have a student at Cornell, Dustin Madison, working on it. And that's, remember, I'll just flash back, that, let me show this one. The relative phase is kind of ratty here. It's also subject to nonlinear oscillations. And the estimates of sensitivity for seeing R modes from a rotating neutron star are usually based on the notion that you'll be able to be looking at a perfectly periodic source. So I don't know what the phase, I don't yet know what the phase error will do to those sensitivities. And in fact, the interesting point is that usually the way we deal with time variability is by producing a template to compare the data to. But these are basically chaotic evolutions, and there's not going to be a template. Yes, Mark?
Will any of the individual spikes be big enough to basically be detectable as a burst?
That's an interesting question. I haven't really thought about it, but it's conceivable.
Because, I mean, there's some, maybe it's brain, there's some minimum threshold for what you can see in LIGO above the noise without.
Oh, no, they won't be that big. I mean, you still need to take, to use the periodicity to be able to pull it out. And so I don't know the answer. Okay, do I have any time left? A few minutes? Okay. So let me talk about the spinning up case, because that's actually interesting too. So there are several phases that we get. The first phase is you spin up to the stability curve. The second phase is the R mode grows to the parametric instability threshold. Then well, it's actually phase 1. I think I numbered them, 0, 1, and 2. Then in phase 2, you get to quasi-steady heating. And I say it's easy because that makes the calculation a lot easier. And in this case, that parameter delta tends to be pretty big. So actually, as I'll show you in a second, that approximation is ridiculously good. And then you go to heating equals cooling. And you have several possibilities in phase 3. You're going toward heating equals cooling. But you can have a fast runaway, which I'll show you an example of momentarily. You can go into a cycle, which is like the cycles that had been described before, but actually much more compact. I think Uri Levin was the first to talk about these cycles. You can go to steady states, and you can have slow runaways. So you've got a lot going on. So to show you that this quasi-steady thing really works, here is temperature in units now of 10 to the 8 degrees over time scales like 10 to the 7 over delta omega, so very long. And the line is the full evolution. The dots are assuming steady state. And this is a runaway because you can see that something is really going wrong here. And what's going wrong here actually is the delta is going to infinity, so you're exceptionally stable linearly, but the amplitude in steady state is becoming infinite. And so you just run away. Now what's shown over here, and this is a partial answer to what you were asking, Chris, is here is the second parametric instability threshold for that problem. And presumably it would not be at this special point that was running away, and so you would stop at that point and try again to be regulated. Okay, I think I'll skip that. This shows runaways. Here's a heating equals cooling curve. If you can go over it, you're going to run away. If you go just below it, you get into a cycle. If you hit it and go down, you can hit a steady state. If you hit it and go up, you can hit a steady state. But you can also hit it and go up and get to the top and run away. So that's this last one this is a fast runaway, and this is a slow runaway. Fast runaways happen on the R mode instability growth time, so it might be seconds or perhaps 30 seconds or maybe an hour. The slow runaways are actually thermal time scales, and they can be 1,000,000 years. So you can spend a lot of time doing this. Okay. This is just to show that when we get cycles, they're compact in the sense that they don't cover a wide range of spin frequency or temperature. Cycles people had talked about before were much bigger than that, and they last a long time. Okay, I'm going to close up in just a minute or so. I did want to say something about the work that another former student of ours, John Drew Brink, did, because it also has something to do with what happens when you have a lot of modes. So we assumed small amplitudes because we figured resonances would keep you at small amplitudes, mode-mode coupling as before. We went up to L equal 29 in the space of these inertial modes, and that was just short of 5,000 modes. These modes have, if you count them up, about 1 billion couplings. Now, out of those billion couplings, only about 150,000 were directly to the R mode. So the R mode only couples very sparsely to the other modes, even in a C this big. We decided not to use all of these couplings because it was impossible to do it. So we cut out the modes that were not close to resonance. And so we checked how robust the results were when we changed this detuning cut. And this knocked us down nicely to only this many couplings, only about 1.3 million. We did use Maclaurin spheroids a la Bryan in 1889. So, and unlike the stuff I was showing you before, there was very simple viscosity, just shear viscosity. It's easy to calculate. That's why partly we did it. The others are more complicated. No accretion, no thermal evolution, no spin change, nothing. And what you see happening is that the excitation, although you have an instability, it's stabilized non-linearly. So I'm sorry these graphs don't come out so well. I don't know why. But this is the amplitude, and the blue is basically blue for C of 4,997 modes. These lines are the R mode, and if you can see it, this is the first parametric instability threshold. And I think the second one is about here. It might be at 1.2. And this is actually at a very small amount of dissipation. High temperature in a neutron star is very small dissipation. And you can see the R mode grows up, but it doesn't keep growing. It basically levels off, and this didn't come out, but this amplitude is it's up here. It's about 1.2 times 10 to the minus 4. So it's a very small amplitude, and it's about the second parametric instability threshold. Okay. So what happens is, in those cases, that the amplitude tends to level off when the rate for the sea of daughters to reach a kind of equipartition is approximately the rate of growth of the CFS instability. And that turns out, roughly speaking, to be around the parametric instability threshold. So to summarize, the R mode instability appears able to limit spins. In fact, I would argue it might do too good a job. There is a problem that was hidden in those graphs, which was how do you really get up to 716 hertz? For LIGO detectability, I didn't talk about the spinning up neutron stars, but they also would be detectable roughly within the galaxy or in the local group. In that case, the problem is that the lifetime of them in the unstable regime is only about a part in 100,000 of their total age. So you're not very likely to catch anybody doing that. For the newborns, if you happen to have one that was born fast and in the local group, then provided that this chaotic phase problem I alluded to isn't a very big limiting factor, they may actually be detectable sources. And potentially that would give you some information about the interior dissipation of neutron stars and therefore indirectly about their interior structure. Thank you. Yes, Lon?
Usually people talk about background gravitational sources, plotting with omega gravity
Yes.
versus frequency. And Wagoner, by the way, did his points, what his effect there. Did you try to do it for background?
No, I haven't, and that's a really good thing to do. Now, of course, these are also high frequency, but Bob's would have been also. No, I haven't, but maybe I'll do it tomorrow.
So inertial waves are infinitely dense
Yes.
spectrums, right? So if you find this ordered pair to give you a high amplitude, you want to go to the next ordered pair. So when you say you want to keep looking at the same ordered pair and they have different delta value when you're defining the damping versus tuning versus damping, you would think there's always a pair which with the delta equals 1 is the most important one under any circumstances.
Perhaps. Let me answer a different question, but not unrelated. So you'll see this number. So I'm going to presume that delta equals 1 is actually also not so far from the minimum parametric instability threshold. Okay. And so actually, if you look at the paper, I will tell you it's really good for me to give seminars at places like CITA because it forced me to try to understand things in my own papers that I don't understand. So here's one I didn't understand. So we have a nice probabilistic argument for why delta, we took delta omega to be a couple by 10 to the minus 4. Why is that a good number? because we have a certain number of modes, and if you ask what, with that many modes, what the small probability distribution is of the smallest delta omega, it was about 2 by 10 to the minus 4. And we had the notion, which is true of low dissipation, that that's the number. The kappa is they range between a tenth and 10. So, I've done string cosmology, that's one. See that they must all be the non-Gaussianity confidence or really pissed at me for saying that. But that's considered one, right, Mark? I mean, that's what Henry would say. Henry 0.1 to 10 times 1. So it's delta omega that determines, roughly speaking, the amplitude. And so we said that that's reasonable. But actually it isn't, because it's sort of gamma daughter squared plus delta omega squared that determines the amplitude. Gamma daughter squared is going up. Delta omega expected is going down. So there's a sweet spot somewhere in there. And I'm not sure where that is, but it's probably around where we are sitting. So we could go to a higher mode number, which would have a lower likeliest delta omega. But it would have a much higher dissipation and hence a larger parametric instability threshold. So I think what tends to happen in terms of delta is that it looks from the simple integrations that you do that you get into some sort of nonlinear cycle, even when you're not linearly stable. And I hesitate to say, because it really isn't something I'm expert in, that these are limit cycles or what people see. But you can actually see periodic doubling and those sorts of things happening when you solve these equations. I'm a total class. So yeah, I think you can have it, delta equals 1. I think you're going to avoid delta very large, because those are then grown to large amplitudes and saying, I want to excite my daughters. And any of the daughters can excite daughters, as we saw in the stuff that John Drew did. But to me, the lesson of that was, and that was a case where we actually had very large deltas, because we had very low dissipation. But nevertheless, you don't seem to get much beyond the first parametric instability threshold, the lowest one. So that when you start the nonlinear show going, it seems to kind of shut itself off. And I think that has to do with the sparseness of the coupling of the R mode. So what it does is it excites the daughters, and the daughters shove their energy into their granddaughters. But it's more important than the R mode growing up and exciting another one of its sparsely coupled modes. So there is some form of energy trapping, if you like, in the R mode, because it doesn't have a lot of coupling. But you still get a cascade, because the daughters engender granddaughters and engender great-granddaughters. And so.
Okay, I think we should maybe continue the discussion upstairs.
Oh, cookies.
Yes. Okay, so let's thank Ira again.